All right, hello, this is the Physics First Interim Assessment 2 study guide. As you can look at this, I don't typically print in pink, but the blue, I guess cyan, has run out as I printed, so not all the colors will look exactly like yours. All right, so Mastery Week starts Wednesday, December 12th. You'll start taking your IA2s that day, some of your electives that day as well. The Physics 1 IA2 will be Monday, December 17th, and I'll be inviting you to those classes or sending codes later in the week, probably on Tuesday, December 11th. Well, let's get started. So we'll go over this PowerPoint in class, but I thought I would also do this as well. Those of you making up grades, these videos seem to have helped as I look at the number of viewed topics and see the kind of work you're turning in, and then see the test scores that follow. All right, don't miss this, just so you know how to focus. 12, Newton's laws of motion. So I want to make sure we spend some extra time on there. What's next? 6, one-dimensional motion and motion graphs. So 6 plus 5 is 11 and 12. So a third of it is one-dimensional motion and motion graphs, and then a third of it will be Newton's laws of motion. And then, of course, the other ideas. 4 questions, two-dimensional motion. As you'll see, I think there's only one formula, and then the ideas that you need to know for that. All right. These questions are very much like the tests. On another copy I have, I actually went through the test and put the numbers. Like the number 1 here is very much like the number 1 on the test. I'm not going to continue to do that, but I just want you to know, as you've seen before. So every now and then I'm going to add something you may want to jot down. Speed is a scalar, which means that speed does not have a direction. Scalars have magnitude only. Speed limit sign says 65 miles per hour. It doesn't tell you which way to go. It tells you can only go 65. It gives you a magnitude only. Velocity, on the other hand, is a vector. So we look at that speed and we add direction. On a motion graph, this might be positive or negative, going in a positive speed or a negative speed. It doesn't always have to be north, south, east, west. It could be left or right. Okay, so question 1 is going to come from these ideas with a little help from those S's, right? Other scalars, mass, right? It doesn't need to have a direction. Distance, how far did you go? Well, I just ran 10 kilometers. I just ran 6 miles. I'm not telling you which direction I'm going. On the other hand, vectors include weight. Weight is always down towards the center of the earth. And displacement. I've gone from this place to another. So a great example is my running. Right? I might run a 10K, but my displacement's 0. I start in my driveway and I end up back in my driveway. It's like I've gone nowhere. If you catch me at the right times, you see me standing in my driveway and you see me standing in my driveway again. Okay? Mass is the same everywhere. Weight changes. The scalar and vector gives us all sorts of information. I think already in class we've talked about not really particularly liking this third picture, but it would appear that these two people are running with the same speed, running together in the same direction. These people might be running at the same speed, but the gentleman's running to the right and the lady is running to the left. And this third picture is a little bit problematic. They're both running up, but their weights are different. So we could even look at a two-dimensional motion here. I'm not sure what to draw for y'all. Like how much of her force is going to the right and how much of her force is going up, and the same with the gentleman. And in this case then, running up this hill, their direction and actually their speed might be a little bit different. But again, I'm not sure I like this picture for us. And because I don't like it, I wouldn't choose anything like that on a test, right? In which picture below do the people have the same speed and the same velocity? They're going the same magnitude, and then they're going in the same direction. So both speed and velocity. Same speed, same magnitude, different direction, and therefore different velocity. Number 3, a person began running due east and covered 15 kilometers in 2 hours. What is the average velocity of the person? And there's even a hint here. So like I like to do, the givens, kilometers is a distance. Hours is a time. My unknown is in the question. What is the velocity? I don't know it, so I'm going to put a question mark. What is the formula? Well, that's the hint, but notice v dt. I knew that was coming. Velocity is a change in distance over the change in time. So I will substitute. I don't know the velocity. V equals question mark. D is 15 kilometers, and the time is 2.0 hours. So I solve. 15 goes into 2. I guess that would be 7.5. Notice kilometers per hour. I know I've done something right because kilometers per hour is a velocity or a speed. Okay? But that's not the correct answer. That's actually a speed, right? Let's think about questions 1 and 2. That's actually a speed. So the correct answer is a person began running due east has covered 15 kilometers in 2 hours. So 7.5 kilometers per hour east. Okay? I want you to know that 7.5 kilometers per hour is wrong. That is a scalar, right? That, in this case, is a speed. Question number 4. Using the on-the-highway distance time graph, which of the following statements is true about the car's trip? Well, let's look. After 1 hour, he's gone, what is that? 80 kilometers. After 2 hours, he's gone, I don't know, what is that? 150, 160 kilometers. After 3 hours, he's gone just over 200, 220 kilometers. So this car is moving. The car does not move. I know that one's wrong. The car travels at a constant velocity. I'm not sure about that yet. The car's velocity increases constantly over time. The car's velocity decreases constantly over time. Well, so we've got to look at these. Now, there's a couple ways that we can think about it. On a distance time graph, you might have simply studied, in that graphic organizer I gave you, a straight line on a distance time graph is no motion. A slope, like this one, is constant velocity. A curve on a distance time graph is a change in velocity or an acceleration. Constant position, constant speed, acceleration. You could simply just memorize this as you look at this graph. Remember, we're going to rearrange these questions slightly on the IA2. All right, well, there's another way to look at it. It would appear that every hour he's going, I guess that's about 80 kilometers. 80 kilometers, I said 150 or 160. It's another 60 plus 80, so it looks like he's going 70 or 80 kilometers every hour. Well, we could check that out. Here's a nice point. Notice this point as we go forward in the test. I know that exactly. That's 4 hours and 300 kilometers. The other point I have is 0, 0, right? 0 hours. So velocity equals change in distance over change in time. The distance he traveled is 300 kilometers. The time he traveled was 4 hours. Notice I've got a velocity. 300 divided by 4. Oh, it wasn't 70 or 80. It was actually 75 kilometers per hour. So that's actually, I guess, 75. And 75 plus 75 is 150. That makes sense. 150 plus 75 is 225. That makes sense. 225 plus 75 is 300. Notice he's going a constant speed. So that's another way to look at that. Well, look here. Using the on-the-highway distance time graph, what is the average velocity of the car? Hint, use slope equals rise over run, or V equals D over T, right? So rise over run. Change colors. Rise. You rose up to 300. Rise over run. You went 4 hours. Rise over run. 300 divided by 4 is 75. So actually, we talked about this one 2 different ways. And good test taking skill. Number 5 helps you answer number 4 as you think about these points. Number 6. Which best compares the motion of dots C and D? Now remember, I said this is a ticker tape thing. This comes from old labs we used to do. If this were a car, there would be at the back of it on a little timer every second, the little point would go down and hit some carbon paper, if you know what that is, leaving a little ink trail, okay? Well, think about it. We'll do the easier one first. I'm going to go ahead and do D. Every, what is this? 1, 2, 3, 4, 5, 6, 7, 8. That might be setting for time, but every second, I'm sorry, I misspoke. Setting for centimeters or something like that. Every second, it went about 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So every second, that little ticker tape thing came down. So this one is constant speed. And as this one moves left to right, notice this one's numbered, right? It didn't travel far. 1, 2, 3, 4, 5. I'm not quite sure how to count that because it's in the middle, but about 4 or 5 centimeters. But the next time, it's more. I think that's 8, and even more, and even more. So this one's speed is increasing. It's accelerating. So this one probably has, since it's all we've talked about, a constant acceleration. Now this is not on the test, but let's just go ahead and think about this. Constant position, that thing would just keep making a point, making a point, making a point. Constant speed, every 8 centimeters, every second, these are all equal. And this one's speeding up, right? And then get closer and closer if it was slowing down. Both C and D are speeding up. No, D's constant. Both C and D are moving at a constant velocity. Nope. C is speeding up. C is speeding up. That's true. And D is moving at a constant velocity. I think it's C. Let me be sure. C is slowing down. No, those would get closer and closer. That's not right. And D is moving at constant velocity. Well, we figured that out, but the answer is C with the ticker tape. What is the acceleration of a car that reached 10 meters per second in 2 seconds? And again, our hint. What is the acceleration? So given, I've got a V of 10 meters per second. Now, you can get this without me telling you this, but wanting to go forward well, that really should be change in velocity over change in time. So this car reached 10 meters per second. So I guess it started off at 0 meters per second. So that's actually the final velocity, and the initial velocity would have to be 0 meters per second. And it did it in 2 seconds. We don't normally do final and initial with time like we've talked about, because we almost always start that stopwatch at 0. Unknown is acceleration. A equals question mark. All right, so what formula am I going to use? Well, it tells me, and notice A, I want acceleration, they gave me a velocity, and they gave me a time. I didn't need that hint, right? It's on your equation sheet. Where is your equation sheet? What's the only one with A, B, and T? And there it is, right? So I substitute. Now here's where I want that final minus initial. It's always final minus initial, because if it went from 10 to 0, if it stopped, it would be 0 minus 10 and be a negative number. It's not going to be a negative number here. So he ended up going 10 and he started off at 0. So I'm going to end up with a positive acceleration. And that might be important on a test question. So solve. Well, 10 minus 0 is 10. 10 divided by 2 is 5. Meters per second per second. Meters per second per second. That's an acceleration. The speed is changing every second. Well, we don't write meters per second, we write meters per second squared. Okay, that answer is kind of hidden, so let me just put a red box around it. Question number 8. If the car started at 30 meters per second and slowed to 10 meters per second before reaching a stop sign, what sign does the acceleration have? Well, here's where I want you to think about it. Hopefully you just know, but the true formula is A equals change in velocity over change in time, and that is always the final minus the initial over some time. Well, the final, it went from 30 to 10. The final velocity was 10 meters per second, and the initial was 30 meters per second. So I just want you to see, it's not magic. The formula always tells you 10 minus 30 is a negative number. If you slow down, this is pretty much what you need to know in Physics 1. If you slow down, that's a negative velocity right from the formula. Okay? Initial, the final. Final minus initial, always in all formulas. I don't know a formula that's any different than that. Number 9. Using the velocity time graph, which statement best describes the difference between the two cars' acceleration during the trip? Well, let's go ahead and be good test takers and read through this. This is a velocity time graph, right? Change in velocity over change in time. Change in velocity over change in time. Rise over run. Read your graphs. This is a different graph. So notice the red one, he's going 1 meter per second. He's going 2.5 meters per second. He's going 4.5 meters per second. As time goes on, he's going 6 meters per second. He finally gets up to 8 meters per second. Notice what he does. Very quickly. Slows down. So in the next second or two, he's back down to 2 meters per second, and he finally comes to a stop. So he's going fast, slows down very, very quickly, and comes to a stop. Blue never stops, right? This might be the tortoise and the hare. The hare quick, and slows down, think it's going to win the race, right? And comes to a stop. And here's that turtle just going about its business. It's going 1 meter per second. It's going 1.5 meters per second. It's going 2 meters per second. It's going almost over 2 meters per second. And it finally makes itself up to 3 meters per second. Notice the blue never stops. Just keeps accelerating. All right. That velocity keeps going up. If I drew some points, if I thought about points along the way. Acceleration 1, that's blue. Acceleration 1 accelerates throughout the entire trip. Acceleration 2 does not accelerate during the trip. That I like A. Okay, test taking skill though. Let's keep reading. Acceleration 1 accelerates throughout the entire trip. Yeah, they're accelerating the entire trip. The acceleration 2 does not accelerate during the entire trip. All right, B. Acceleration 1 rapidly accelerates and then stops. No, that's the wrong one. The red one did that. Acceleration 1 has a constant rate of acceleration, is what we spoke about. Acceleration 2 accelerates at different rates during the trip. Well, now I kind of like A and C. D. Acceleration 1 accelerates for the first 2/3 of the trip, and acceleration 2 has a constant rate of acceleration. Acceleration 2 has a constant rate, the red one. No. So we cross these off. All right, so now we're stuck with 2 that look good. Acceleration 1, Accel 1, accelerates throughout the entire trip, faster and faster and faster. Acceleration 2 does not accelerate during the trip. Acceleration 1 has a constant rate of acceleration. I like that phrase, constant rate of acceleration. Acceleration 2 accelerates at different rates during the trip. I might write this test question a little bit differently, but C is the best answer. Constant rate of acceleration and accelerates at different rates. Okay? All right. Acceleration 2 does not accelerate during the trip. Well, actually it does. Let's go ahead and cross that off. I'm going to rethink that. Yeah, definitely C. All right. Please read all the questions. You're going to read something that makes sense. Okay? Keep reading all the questions. Question 2. Sally walks 10 meters forward and then 10 meters backwards. So I'm going to put that into vectors, right? She walks 10 meters forward, some positive direction, and she walks 5 meters back. 5 is half of 10, so hopefully my vector looks like that. I'm going to use the head to tail method, right? Head to tail, just where she started to where she ended. You might have done that naturally, but that's also the way we add vectors. Well, how far did she go? This also might make sense, but we talked about this with vectors. The resultant vector from where you start to where you ended, from where you start to where you ended. Well, that's 5 meters, right? 10 meters minus 5 meters. And she went more right than she went left. She went more forward than she went backward. Different ways to think about this. What is her displacement and what is her distance? Well, here we've been really nice. Displacement, magnitude, and direction. It's a vector. Distance, magnitude only. Well, like me running out there, she's tired. She just did those 15 meters, right? Okay, I guess I was thinking miles. She wouldn't be tired after 15 meters. She went 15 meters. Displacement, she went from this place to this place. She is displaced only 5 meters. Forward or backward? Well, the correct answer would be 5 meters forward. Just like I did before thinking about your test. 5 meters is the wrong answer. Okay? That would be a good distractor on a test. She went 5 meters forward. That's her displacement. Not backward, she ended up over here. All right, acceleration due to gravity is always, sometimes, never the same on Earth. There's another question that I would rewrite, but we talk about acceleration near sea level as always being 9.8 meters per second squared. And even in advanced placement physics, I'll just tell you, we often use 10 meters per second squared as that number. It's so close. It actually is variable, and this allows us to round up and do some pretty good math. Okay, acceleration due to gravity is always the same on Earth. Okay, thinking about your test, thinking about a next question, right? I kick a football, kick it hard. Right? It goes up. It comes back down. We've talked about the horizontal velocity staying the same. When I first hit it, its vertical component is high, and then it starts slowing down as gravity hits, and it's actually 0 up at the top vertically, not horizontally. And then as it falls, it speeds up. Yo, its vertical velocity is changing. This question is about acceleration. Whenever in projectile motion you're working a problem, acceleration is always the same on Earth, and we use this number, negative 9.8 meters per second squared. You could probably do 10 in your head, y'all, and get to the right answer. A bowling ball is thrown off the top of a building. Determine distance the ball has fallen after falling for 3 seconds. Okay? The gravitational acceleration due to gravity is 9.8 meters per second squared, and they've given you the formula. So that's cool. All right, what is the distance? So, givens, seconds is a time. The acceleration, or gravity, is 9.8 meters per second squared. We normally use negative. We can talk about that. Unknown wants to know the distance. Well, the hint's right there. It's going to be on your equation sheet. It wants to know the distance. It's giving me a gravity and time. And the only formula that we have or will have that makes any sense is this one. D equals 1/2 gt squared. So I'm going to substitute. D is a question mark. 1/2. Gravity, negative 9.8 meters per second squared. Time is 3 seconds. And time alone is squared. All right. Wanting to do this for you again. 1/2 and do 0.5. I'm going to times by 9.8. I'm going to ignore that negative. I'm going to times by time. I'm going to times by time again. Now some of you, I think this will mess it up, you know how to use a scientific calculator. There's no need for that in this problem. For those of you who kind of get freaked out by math, I've said this over and over again, 1/2, 0.5 times gravity times time squared, right? 44.1. Seconds squared. Seconds squared. I'm left with meters. It should be no surprise, right? 44.1 meters. Now, there was a negative, and we should include that. It fell down. It didn't fall up. It fell down. So, of course, if that number were positive in some other calculation, it would be up in the air somewhere. So, negative 44.1. Okay, determine the distance the ball has fallen. Well, it's distance. Remember, distance doesn't care about direction, so I don't really have to care about that negative. Okay, so just kind of be careful of that. We've kind of warned you a couple times that with gravity, you have to decide how you're going to look at that. All right, your own high-speed digital camera. We can take a picture every 0.5 seconds. Use the picture from the previous question to help you. You decide to take a picture every 0.5 seconds of the bowling ball being thrown off the building. After you develop and analyze the pictures, you realize that the distance the bowling ball falls in each new picture is. Well, test questions often help. Look at that. This is another drawing we had on a different test. It should be no surprise. Distance, we'll call that 1, and distance 2, distance 3. Right? Notice the distances are getting greater and greater as that bowling ball accelerates. So you can actually look at this problem to help you remember how to do this. The same in each picture. Well, I forgot the question. After you develop and analyze the picture, you realize that the distance the bowling ball falls in each new picture is the same. No, it is not the same. Gradually less. It is not slowing down. Gradually more in each picture. Yes, let's keep reading. Proportional to the mass of the ball. We've said this over and over again. And look here, D equals 1/2 gt squared. Mass is nowhere to be seen in that formula. All things fall at the same acceleration, regardless of mass. So you might remember the video of the hammer and the eagle's feather on the moon and other things we've done. 14. Inertia, gravity, momentum is the reason your body seems to push back against the seat as the car quickly accelerates from rest. So, again, you may send me emails about how wonderful my artistic ability is. So here's a guy in his steering wheel, and he's just sitting there at a red light. Red light. Okay. Oh, you know what? Red's on top, so we make sure we can see it. All right. Well, he's at rest. Things at rest want to stay at rest. So that car takes off, right? Boom. That car takes off, and your body, even though you've got that seatbelt on, there's a little bit of play there, your body wants to stay at rest. So it seems like as the car goes forward, right? The car goes forward, your body ends up going back and pushing back. So why does that happen? Inertia. We're actually going to study momentum in January, and gravity is always down. So this is definitely forward for a couple different reasons. 15, and we're half done. Newton's second law states that F equals m times a, force is mass times acceleration. Which example would have the greatest acceleration? All right, you need to do the calculation for these. Let me just tell you, looking at the numbers, I probably would have gotten this wrong. Also, this is a time you've got a question where you have to do a little bit of work on each one. All right, F equals ma. Which has the greatest acceleration? F equals ma. So let's use our triangle. M is by the a. So put the F up there. Which has the greatest acceleration? So a equals F over m. Told you force is always on top, force over acceleration or force over mass. All right, again, I really wish you guys would just use your algebra. It's being multiplied by m, so I need to divide. What I do to one side, I do to the other. Either way, on your equation sheet, acceleration equals force over mass. Force over mass. Force over mass. Force over mass. Force over, force over mass. Well, look at that. C and D are the same answer. 100 divided by 50 is 2. Please note, a Newton is a kilogram meter per second squared. Kilograms over kilograms. I'm left with meters per second squared. I'll just do that once. So 2 meters per second squared. 2 meters per second squared. You might be tempted to grab this one, but the answer to C and D are the same. 0.5 divided by 1, 50 divided by 10. Well, here's your answer. That's going to be 5 meters per second squared. Okay, be careful. It's not necessarily the biggest numbers. It wasn't the smallest numbers either. 16. A 3-kilogram lunchbox is pushed across the lunch table. The acceleration of the lunchbox is 2.0 meters per second. What is the net force applied to the lunchbox? Some of you have already done this in your head, but I'm the teacher and I have to keep teaching. Kilograms is a mass. Meters per second squared, they actually told me, is an acceleration. I am looking for the net force. What is the formula? Well, they gave it to me here. That's nice, but F, M, and A, I know that formula. F equals mass times acceleration. I substitute. Right? Oh, by the way, if you're going to get a 100 on this, I do expect you to show all your work, okay? I'm going to be nice over here, I think. I hadn't thought about it. Mass is 3 kilograms. Acceleration is 2.0. Solve. My colons are looking like equal signs. F net equals 3 times 2.0 is 6 kilograms meters per second squared. We just said in the last one, kilogram meter per second squared is a newton. So that's 6 newtons. You know, I know you may not follow these steps. I really wish you would, especially as we get into new formulas. But I would like to see at least this. Right? So you've got the formula. You didn't have to rearrange it like we did in the last one. Mass times acceleration. So show the steps, and you'll see the units, and you'll be sure of your answer. So this is showing work, I guess, too. Okay. Just want to see something more than just an answer. Find the weight of a 10-kilogram rock. Find the weight. Remember the acceleration due to gravity. Look at this question's negative 9.8. We're not even being consistent on the review sheet. Hint, W equals mg. And again, I don't like that little w, so I'm going to put my force there. All right. Given kilograms is a mass. Right? They're giving me that. Gravity, negative 9.8 meters per second squared. What are we looking for? We are looking for a force. We're looking for weight, and we don't know it. What is the formula? Right? Force equals mass times acceleration, but when we're talking about it, weight, the acceleration is gravity. Substitute. His weight is, or the rock's weight is, 10 kilograms multiplied by negative 9.8 meters per second squared. Solve. Negative 98 kilograms meters per second squared. What is a kilogram meter per second squared? Of course, it is newtons. Why negative? Because gravity is always down towards the center of the Earth. Now, when we report weights, we would just say, hey, it weighs 98 newtons, because we all expect that negative. But I just want you to know that negative reminds us as you do your work. Gravity is always down. In the image to the right, if both people are pushing the box with a force of 15 newtons, tried to make the same length of a vector, right? They have the same magnitude in opposite directions. What will happen to the box? Well, 15 newtons, 15 newtons. I could do vector addition, 15 newtons to the right, 15 newtons to the left, and I'm back where I started. The net force is 0 newtons. Okay, we subtract them. They're in opposite directions. When they're in opposite directions, keeping it simple for us with vector addition, we just simply subtract. It's not going to the right or the left. Okay, they're wasting all that energy. 19. Match the following laws. Well, let's do this. Newton's first law is the law of inertia. Things at rest want to stay at rest. Things in motion want to stay in motion because of the mass. We've talked about the word inertial mass. Kind of want you to put those words together in your head. We're going to get to momentum with that. Newton's second law is actually the law of acceleration. Something at rest, you want to move it, you want to accelerate it, you have to apply a force, right? This is a story, right? Something's in motion one way, you want it to move in a different direction, right? A vector, you need to accelerate it. And we talked about this law of acceleration comes from this formula. F equals ma. You apply a force to a mass, it accelerates. Newton's third law, the law of interaction. Action-reaction pairs, interaction, right? These guys are equal and opposite. I kick a football, that football kicks me back. I sit down on my chair pushes back up. If that can't do that, the chair is going to break, right? These are equal and opposite. Hard to think of a wall pushing, but a wall pushes. Hard to think about my chair pushing up, but my chair better push up or up on the ground. For every action, there's an equal and opposite reaction. That's definitely Newton's third law. A law of motion that states that an object at rest stays at rest and one in motion stays in motion. First law. Remember, the rest of that definition is until acted upon, and that's the second law, acceleration. Right. Which of these would be the best example of unbalanced forces, right? So, quick reminder, balanced. F net equals 0 newtons. Everything's balanced, right? Could still be in motion, but it's going to be constant. Unbalanced. F net equals something, right? It's got to equal something. There's just going to accelerate one or another. Constant velocity, right? The dog is running. He's running against friction. The forces are balanced. You can stand very still during the national anthem. You are pushing down on the ground or the stadium, and the stadium has enough strength to push back on you, right? These forces are balanced, so you are in constant velocity. Your velocity is 0. A snowball, look at this, picks up speed. That's acceleration, isn't it? I'm betting on C, as it rolls down the mountain. D, your coffee cup does not move from its original spot on the desk. It pushes down. The desk is able to push up. Snowball picks up speed. So gravity is working on that snowball, so its weight is pulling it down. Right? Unbalanced forces. Notice A, B, and D are the same, so sometimes in tests you can play the game, which one's different. We're 2/3 done. I think I'm a half hour in. It's not too bad. 21. In order to increase the speed of the airplane below, you will need to add weight, go up a ramp, increase the force being applied? I don't remember this question. That's really kind of odd. Okay. In order to increase the speed of the airplane below, you will need to, I'm not even sure how to explain it. All right. And there's some different problems in my head too. All right. Well, sorry for the pause. I'm trying to think of the test question and I can't. All right. We can assume increase the speed forward would be our ultimate goal and not down towards some horrible crash, right? So if there's drag, maybe there's more drag, maybe there's wind, maybe there's turbulence, we would have to increase the force being applied, right? So let me do this. The thrust, the movement forward, is the applied force. The drag is a frictional force, air resistance, right? The weight, always down, that's why I need to add the word forward just to be sure. Weight is always down, and then you've got this lift. And we really haven't talked about that one. That's another applied force, actually. These shift for the air pressure. But in order to increase the speed forward, right? So we're not looking up, down, we're looking forward. We need to do something with that applied force, that force being applied, that thrust. So going to be applied weight and force. Let's go ahead and do this. That last question had a coffee cup question, so let's deal with a coffee cup, right? And let's say, can I draw a hand real quick? I don't know. So I've got my little fingers in here. There we go. I don't know. Thumb on top. That is horrible. Apparently I've broken my thumb. So I have applied a force to the right, trying to draw the coffee to me, right? Well, what's fighting against me? Whenever two surfaces connect, there is a frictional force. Friction always opposes motion. There is always, here on Earth, weight pushing down. We have a table like this. The table's got to be pushing up or it would fall, and that's the normal force. So applied force and frictional force, in this case right and left, back and forth, and then weight and the normal force, or weight, and in this case some other applied force, up and down. Okay, so think direction as you think about this question. Sorry for my little stumble there. Right. Lift, thrust, weight is a force that works against drag in the image above. Against drag. So we just ended up talking about that. Drag is a form of friction. So the thrust, the applied force, is working against it. Okay. Just like in projectile motion, you think horizontal and vertically. Okay. So the thrust forward, the applied force, those engines working, those jets working. Andre is playing air hockey with Alexa and shoots his puck across the near frictionless surface to score a goal. Draw the free body diagram below that would represent the forces acting on his puck as it glides across the table. All right, so let's think ahead a little bit. Here's my coffee cup with my bad hand, broken finger, or whatever that is, right? But this one says a near frictionless surface. No, nothing's on it, right? It's going forward. It has a velocity going forward, probably pretty fast on a hockey field, right? And so it's near frictionless. There's no applied force working on it. Okay. Well, weight is pushing down always on Earth, and it's not falling. The rink, the floor, is able to push up. And so that's a normal force. Remember free body diagram, we draw a dot, and we draw this back and forth. And this particular problem says frictionless, so I'm not going to draw friction. Now, let me go ahead and talk about the real life. There is friction, right? So just to draw a contrast here, and to keep practicing. There would be a little bit of friction. Notice, because there's friction, these balance out, but there's this. There is a net force. It's really small, but there is a net force, so that thing is going to slow down, right? It's not going to stay constant forever. I showed you a video where it finally slowed down after a long, long time. But if it's frictionless, this would be the picture you drew. Don't overthink it. 24. The force that opposes motion is friction. We just said that. If you want a box to move while dragging it, the applied force must be... You ever pushed a refrigerator by yourself? It doesn't have wheels? You are pushing and pushing that thing. Right, this might be a little bit better than my hand, right? And it doesn't go anywhere. It doesn't go anywhere because whenever two surfaces go, there is friction. And I'm purposely drawing this vector longer. So your applied force, that refrigerator is not going anywhere. Okay, and then when you finally do move the refrigerator, you feel like, if you've ever done something like this, I'll draw a little bit bigger, you are pushing so hard and it's hardly moving. It's moving, but it's hardly moving. And that's because most of your effort is just going against friction. Okay, from where you started to where that ends, you've got this little bit, this net force right here, where you're finally accelerating it to the right. Your applied force must be greater than the frictional force for it actually to move, right? If it's equal to, it's not moving. If it's less than, it's not moving. You have to overcome friction. Think about your car. You're spending a lot of gas just trying to maintain 65 miles per hour. You are equal to all the friction of the tires on the road. All that your parents are doing while they're pushing the accelerator is overcoming friction, so you're not speeding up. Draw a free body diagram of a girl hanging on both hands with a trapeze motionless. So we've done this a couple different times. I forget her name. Seems like she had some cute name, right? So if she is 100 newtons, and there are two ropes, we've got 50 newtons and 50 newtons, right? Maybe it's just a bar with a hoop. Right? So if she's 100 newtons, this hoop and rope better be able to hold 100 newtons, right? So free body diagram. This one, we have an applied force or a tension force from both ropes, and we have her weight, right? And these two should equal this one. Let me draw this a little bit longer. Right? These two equal this one down. This one, different free body diagram. 100 newtons of weight, 100 newtons of tension or applied force. A rope would remain in equilibrium during a game of tug-of-war when the net forces acting on the rope are, well, hopefully we've talked about this in different ways, balanced and zero. In other words, another thought for balanced, right? They're pulling with 200 newtons. The other team is pulling with 200 newtons, right? To the left, to the right, you end up subtracting, and that's net force of 0 newtons. They're balanced. Almost done. When an object is in equilibrium, the net force acting on the object is equal to 0. Static means that the object is at rest, which is an example of an object in static equilibrium. So we haven't used the word static, but it's right there, and you can see we've had questions quite like it. The Earth orbiting the Sun, a book on a table, a boy pulling a cart with a constant velocity, an apple falling from a tree. When an object is in equilibrium, the net force acting on the object is equal to 0. All right. Well, hopefully about this book on a table. The book is pushing down. The table is pushing up, right? Well, look here. A boy pulling a cart with a constant velocity. So he's pulling, he's got some applied force. He's going at a constant velocity, so his net force has to equal, excuse me, 0 newtons as well. So he's got friction on all 4 of these tires. We'll just draw one. An apple falling from a tree. Well, here we have gravity at work, right? So the weight down, so it's weight down. And it's going to get very little, almost negligible air resistance. So this one, it does not have 0 net force. Okay. The Earth orbiting the Sun. I don't know that I want to deal with that one. I'm going to have to look at your test question. The Earth orbiting the Sun. It is at constant velocity for the most part, but we'd have to get into some astronomy on that one. I'm sorry, I think I looked at your test more than anything. I'm going to make a note, 21 and 27. I got to look at those. Hopefully, B and C, I hope you understand. D, those are really good as we've discussed them. And then adding the word forward, then this question makes a lot of good sense. Right, we are almost done. I definitely wanted this less than an hour, so about 45 minutes. Motion in 2 dimensions is motion that has both horizontal and vertical components, which is an example of motion in exactly 2 dimensions. A bicycle traveling forward in a straight line on a level street. Straight, level, forward. That bike, right, that is all horizontal, moving forward. A soccer ball kicked along the ground by one player directly to another. Along the ground, directly to another, right? So, to another player, I don't know, he looks like he's about to fall over, right? So that ball is going directly to the other one. That is all horizontal. A baseball traveling with a vertically arcing trajectory from a batter to an outfielder. A baseball traveling with a vertically arcing trajectory. So we have the word trajectory from a batter to an outfielder. So we have our batter. I'm sorry, I'm already looking at D. So he hits, it's arcing to the outfielder. He's waiting, right? So we have that trajectory, yes? So there is the projectile, there is its trajectory, and it's in the shape of a parabola. You remember all those words. So that's definitely in 2 dimensions. This is something else I hadn't caught. It's rising into the air and veers right. Well, we haven't talked about this at all, but it's kind of cool in physics, right? So we think vertically and horizontally. Well, this is what you get to later in college. X, Y, Z. When you get into physics in college and you're thinking about robotics and moving, so it is an airplane taking off from one way that simultaneously rises into the air. So that plane is going down the runway along Z, right? It's lifting, so it's going along Z, it's lifting Y, and then it veers to the right. So this is actually a 3-dimensional situation we got going on this one. 2-dimensional, 1-dimensional. All right, 29. The horizontal component of the projectile's motion is constant or accelerated, but the vertical component is constant or accelerated. But you better not answer with the same answer. But, right? So horizontal is constant because we ignore air friction. The vertical component is accelerated because there is gravity. And number 30. If the center on a high school basketball team wants to increase the maximum height of his jump, jumping with greater initial velocity would increase, decrease, not affect the height of his jump. Greater initial velocity would increase the height of his jump, right? But he jumps. Now, the trick is if he can jump at a 45-degree angle, depending on what he's doing, that 45-degree angle we've mentioned in class just briefly, that gives you the furthest distance, right? Well, basketball is a little bit of a different goal, right? You want to get higher, so you try to jump at a different angle. But if you can increase your velocity, you're going to get higher regardless, because some of it's going to move you forward, right? And some of it's going to move you up and accelerate you upward. So number 30. All right. If this didn't record, I will be crying. Hope that makes sense. All right. Thank you. Sorry for missing class on Monday. This is my help to you. We will look at this in class on Tuesday if you would like.